if you react iron with oxygen in the air in presence of moisture, you get rust. This is a balanced formula where you have 4 ions, 4 moles of ions on the left. You have 2 times 3, 6 moles of atomic oxygen. And here you have got 3 times 2, 6 moles of atomic oxygen. So you have a balanced chemical equation. Let's look at the masses involved in this equation. 4 moles of iron, every moles of iron, 56 grams. So 56 grams times 4. It's 55.9 something. So it adds up a little bit. Fraction, or 223.2 grams. That's total mass of 4 moles of iron. And then you have 3 moles of oxygen. Every mole of oxygen is 32 grams. If you multiply 32 by 3 times 32, you're going to get 96. So total mass of reactant has to be 319.2 grams. Add 96 to 223.2. And what is the mass of product? 2 moles of Fe2O3. If you multiply 2 by molar mass of Fe2O3, you should learn how to calculate. I don't want to go through that. You're going to get a total of 392 grams of product. So do you see mass of what you start with is equal to mass of what you end up with? This is a proof of the law of conservation of mass. Any questions, guys? So I'm going to go to the next slide. I'm going to take a look at the same equation. Reaction of iron forming rust. Reaction of iron with oxygen in the air forming rust. Guys, is it possible to look at number of the moles in this chemical equation and relate reactants and products together? Or is it possible to relate number of moles of reactants, different reactants together? For example, if I ask you, what is relationship in this equation? What is relationship in this equation between number of the moles of iron and oxygen? What would you say? Moles of iron and oxygen. Do you see every 4 moles? Remember, these are balancing coefficient. They refer to number of moles. Can you see that 4 moles of iron, that's what this says, is going to need 3 moles of oxygen to give you the right product? Can I say the reaction, the ratio between number of moles of iron and oxygen is 4/3? Can I say that? This is a conversion factor. Remember, conversion factors are equal to 1. You also remember that we can always have 2 conversion factors. Relationship between the first one and second one, they are inverse of each other. In other words, take the bottom to top, take the top to the bottom, you have the other conversion factors. They're both equal to 1. So by looking at this chemical equation, I can write 2 conversion factors between number of oxygen, number of moles of oxygen and iron.
Hey, Mr. Fard.
Sir.
Is the bottom equation or the conversion factor? Is it supposed to say 3 moles of oxygen and then?
Are you talking about this one?
Yes. So the red, should the one in red have 3 before the oxygen?
Okay, let's look at this one. So you're okay with this first line, yes?
Yeah.
Okay. Let's look at second line, and then I'll answer your question when I get to the third line.
Okay.
This is second line, and this is third line, and we do it together. Guys, what is, let me clear these. It's not confusing. So if I'm going to find out the relationship between iron, number of moles of iron, and number of moles of rust, iron 3 oxide is rust. Do you see every 4 moles of iron is going to produce 2 moles of Fe2O3? 4 and 2, yes or no? 4 and 2. This is one of the conversion factors. What is the other conversion factor which relates these two together is take the bottom to the top. Take the top to the bottom. So these are 2 conversion factors which can help you to relate number of moles of iron to iron 3 oxide. These two are related by these 2 equations. Is that acceptable to you so far? Do these make sense? If yes, I'm going to look at the third equation. We are trying to understand relationship between number of moles of oxygen and Fe2O3. So this is oxygen and this is Fe2O3. Can I say every 3 moles of oxygen can produce 2 moles of Fe2O3 based on these 2 numbers? And if I want to write the other possible conversion factors, all I have to do, inverse the ratio. Take the bottom to the top and top to the bottom. Both of these are conversion factors that are equal to 1, so inverse of 1 is 1. Does this make sense? Was it Caleb?
Yeah, it was me. That makes sense.
Okay, thank you, Caleb. Anybody else who has question on this? Is this clear? Any questions? So I go to next slide. Go guys, I want you to do this question based on what you just learned. Raise your hand when you're ready, please.
Can you hear me?
Yes.
I have a question.
Yes, dear.
If these are conversion factors and we're finding the conversion, what are we converting to? Like, what's the end goal of converting? Are we just trying to understand the relationship or?
No, I'll show you the application.
Okay.
If I say we are using 6 moles of hydrogen, how many moles of nitrogen do you need? You have to use this. And if you have moles of nitrogen, then you can give me the number of grams.
Oh, okay, I get it.
So it's used in calculations, and I'll give you example pretty soon, and you will do problems. That was a good question. Thank you. You made good progress, guys. If I go next slide, is this what you got? If not, ask me to explain more. Did you get these 2 relationships?
Is this always true, Mr. Fard?
It is always true when you have a balanced equation.
Okay.
So you must have a balanced equation to deduct it from. Do you see when there is no number here, what does it mean? If
1.
I don't have a coefficient, what does it mean? What's the number when I don't have coefficient? Anybody?
1.
Good job. Yes, it's 1. So we don't write 1. So can I say every 3 moles of hydrogen needs 1 mole of nitrogen? And if I'm asking relationship between NH3 and H2, this is NH3 and this is H2. This is fair to say if you want to make 2 moles of NH3, you need 3 moles of hydrogen. That means we are assuming you have enough N2 to react. How many moles of hydrogen do you need for 2 moles of NH3? Then you can answer the number of moles, and of course you can convert number of moles to grams. Then you have a gram relationship, mass relationship in a chemical equation. Do you have any question? Don't be shy, guys. Ask, please. So let's see if we can clarify this. Show the application. It says, consider the following reaction. How many moles of Fe2O3, that means how many moles of this, are produced when 6 molecules of O2 is used? 6 moles of O2 is used. So what is problem giving us? Is problem giving us number of moles? 6 moles of O2 is going to produce how many moles of Fe2O3? That's the question, right? Can I say, do you see a change of unit? Do you see that we are converting moles of O2 to moles of Fe2O3? The answer should have moles of Fe2O3. So I must use a conversion factor to cancel moles of O2. I must cancel this and convert it into moles of Fe2O3. So you can figure out what sort of conversion factor you need. You always write the unit you are canceling on the bottom. So this must go on the bottom. That's what we want to cancel. The unit you are converting into must go on the top. So can I say we are starting with 6 moles of O2. I want to cancel moles of O2. I write that on the bottom. I write moles of O2 on the bottom. I want to convert to moles of Fe2O3. I write moles of Fe2O3 on the top. Remember, the third step in writing a unit conversion factor is always relating top to bottom. So if I ask you, what is relationship between number of moles of Fe2O3 and O2? Can I say every 2 moles of Fe2O3 can be produced from 3 moles? So the ratio is 2 to 3. Where are they coming from? 2 is coming from here, and 3 is coming from here, from our equation. So if I do this calculation, what are conversion factors suggesting? Cancel moles of O2, you will be left with moles of Fe2O3. That's what you are left with. How about numbers? What is it suggesting? Multiply tops with top. Get the answer, divide by the bottom. 6 times 2, 12. Divide by 3, you get 4. So 4 moles of Fe2O3 would be produced if you use 6 moles of oxygen. Anybody, do you have any question? Please ask. Anybody? Okay.